Now, when they said, right, draw lines to represent gravitational field, so what you do is, now, forget about what I did just now, so many lines. The answer is only the blue color line up to the surface. That means what you draw, right, to be neat, right, draw one line here, horizontal, another line horizontal, to the surface enough, don't draw inside. One line vertical to the surface, another line vertical to the surface, and then diagonal, another 1, 2, 3, 4. That's it. Don't draw more than that. No point, and it becomes very messy. Now, you don't have to extend it all the way to the center to show the intersection. You don't have to. That is only to explain to you why we can treat this as a point mass. That means, you see, remember I told you Newton's law of gravitation is only for point masses? Now, why is it, even though it is a sphere, we can treat it as a point mass? Because if I extend the line of action of gravitational field lines of all these lines, where do they meet? Middle. So they all seems like they're all meeting at the center, so it looks like a point mass. But that is only for your understanding why we can treat it as a point mass. You don't have to draw up to the center. You must draw up to the surface. Understand? Now the second part says a second sphere has the same mass but a smaller radius. Suggest what difference, if there is, between the patterns of the field lines between the two spheres. Now what it is essentially saying is, let's say I got a smaller sphere. Can you see I drew a smaller sphere? But it's the same mass. It's just the size is smaller, but it's the same mass. Will the field line patterns be any different? Now, why not? Okay, the logic is this. Imagine I had a small test mass. This is a test mass. I'm talking about the original sphere. Original sphere. This is a test mass. Between the center and center here, to find the force, I must use F equals to G mm over R squared. But the R, because you must treat it as a point mass, you must always take from center to center. That means for this sphere, the center, for this sphere, the center. So center to center. Do you understand? If I replace this sphere with a smaller sphere, but same mass, is the center of this smaller sphere the same as the center for the big sphere? Same. If I calculate the force, will I get the same answer? Yes, because the mass is the same as before. The distance from center to center is the same. So my point is, the force acting on the test mass is the same. So the field strength at this point must also be the same. So therefore, the pattern of the field lines must remain the same. But there's a small difference though. If I have to draw the field lines for the smaller sphere, can you see I will end up drawing to the surface? Which is now, when I draw to the surface of the smaller sphere, can you see the lines at the surface here are closer together? The lines for the bigger sphere, can you see this is quite big spacing? But for the small sphere, can you see these lines are closer? That's the only difference. So how do you put it in words? You can say this. The number of field lines will remain the same. The number of field lines will remain the same. But the lines will be closer. But the lines will be closer near the surface. But the lines will be closer near the surface of the smaller sphere. But the lines will be closer near the surface of the smaller sphere. Now, for this question, when they said Newton's law of gravitation, now, you know how to get the 2 marks. The first mark is for saying for point masses. Then for second mark only, then you will say the force means every mass will attract every other mass with a force that's directly proportional product of their masses, and it will say proportional to the square of the distance apart. Although sometimes they will just give you 2 marks without saying the point masses, but better write the point masses. Sometimes got 3 marks also. For 3 marks, definitely 1 mark for point masses. Alright? For 2 marks, a bit risky if you don't write for point masses. So you go back and do that, no problem. Just copy from the notes. But the one I want to explain to you is part 2. Explain why, although the planets and the sun are not point masses, the law also applies to the planets orbiting the sun. So what they're trying to say is this. If you are using Newton's law of gravitation, which is supposedly for a point mass, meaning to say the whole mass must be considered to be a single point. How come we can treat the Earth and the planets and the Sun as point masses, but they're not? Because you look at the Sun, how big is it right now? Can you say, oh, I just assume you're a dot? They'll be insulting right now. You say, oh, Brian, no, you are just a dot. It's insulting, but how come I can treat you as a dot, or I can treat the Earth as a dot, or treat the Sun as a dot, even though it's such a huge sphere? Right. So the answer lies between these. Now, if you're talking about small distances, like for example, let's say you got two masses here. So if I take the distance from center to center, treat them as point masses, it will be different from if I take surface to surface right now. Is the distance the same? So there'll be an error right now if I take center to center right now. But if they're super far apart, like very, very far apart, then the difference is just a small percentage of the actual distance. Do you understand? That means if they're very far apart, let's say the error is 2 meters. If the distance is 10 meters, error of 2 meters is 2 over 10 is how much? 20% error. But if your error is 2 meters, but the distance is 100 kilometers, that error is insignificant. You understand? So if they are very far apart, like the Earth and all the planets to the Sun, are they near or far? So you can treat them as just point masses. It doesn't matter anyway, because the error is small. Okay? So you just say, the only part you say is their separation is very much bigger than their radius. So for this question, if you want to find the mass of the Earth, you notice what field strength they gave, the field strength of the Earth right now. Now they want to find the mass of the Earth. So the question is, the mass of the Earth here, the field strength of the Earth here, that means you want to find the mass that produces the field. That means the more important mass or the less important mass? More important. That's why you must use this, because the M on top is the more important mass. Do you understand? So this big G is given, don't have to memorize, but the formula, yes, like you're gonna memorize this now. So substitute the field strength at the surface 9.81 here. Then you can substitute the radius. Don't forget there's a square. Then you can find the mass of the Earth. So the definition of gravitational field strength is simply force per unit mass. That's it. Now for part B, you need to understand something. The radius is R. The mass of the star may be considered to be a point mass at the center of the star. That means you can use all the formulas for point masses. Oh, by the way, can you see this field strength GM over R squared? This is only for a point mass. And all the formulas like GMM over R squared, GM over R squared, all the R1, all these are for point masses. That means it must be taken to be a single point. Like for example, if you say the star has radius R, that means you treat the whole sphere, the mass to be in the middle, and then the distance from the middle to the surface is R also. So they gave you the field strength at the surface is GS. So can you see at R, they started with R, this is GS. Can you see all? Now you must plot the graph of how the field strength changes from R to 4R. Now you don't simply sketch, no, you must calculate one, no, because there's 2 marks here. There must be some accurate plots on that. So what do? We use GM over R squared. So why use GM over R squared and not F over M? F over M no R, so you cannot see the relationship lah. Anyway, when you use GM over R squared, the good news is G and big M are constants. So therefore your G is just inversely proportional to your R squared. Do you understand? So how do we solve this? Very simple. When you double the R, when you substitute 2R inside here and you square it, isn't it 1 over 4? You mean your G is 1 over 4? That's why it's G over 4. If we substitute 3 here and you square it, isn't it 1 over 9 overall? You substitute 4 here, you square it, it's 1 over 16. So you have to calculate, like for example, at 2R G over 4 is 0.25 G. So you know what it did? Can you see this point is about 0.25 G? Because 0.2, 0.4, 0.3, so 0.25 somewhere here. You see that? Similarly, for 3R, so G over 9 is about 0.11 something. So this 0.2, 0.1 is somewhere in the middle, so somewhere in the middle. That's your 1 over 9. Then calculate your 1 over 16 and then you plot here also. Right? Then only you join a nice smooth line like this. So what you have here is you have the Earth and the Moon, and then they ask you, explain why there's a point between the Earth and the Moon at which the gravitational field strength is 0. That means there exists, right, somewhere a point between the Earth and the Moon. That when you stand somewhere there in between the Earth and the Moon, then suddenly you're not moving because the resultant field strength is 0. So how can your resultant field strength be 0 here? Okay, I'll show you. I told you guys before, field strength is vector or scalar? Vector. Just like your electric field strength in your AS is vector or scalar? Vector. In electric field strength in AS, direction of field strength follows what direction? Force acting on a positive test charge. For gravitational field strength, the direction of gravitational field strength follows the force acting on a test mass. Test mass. What I'm trying to say is, for example, let's say I want to find the direction of the gravitational field strength of the Earth at a point somewhere here. So to find the field strength of the Earth, let's say here, I must put a test mass here lah. And I will ignore the Moon for a while because I want to find the field strength of the Earth. I ignore the Moon for a while. I put the test mass here. Will it be attracted to the Earth or repelled? Attracted. So if the test mass is attracted to the Earth, that means the force on the test mass is to the left. The field strength must be also to the left.
Why attracted to the Earth?
Why attracted to the Earth? Because mass and mass will always attract according to Newton's law of gravitation. Because I'm ignoring the Moon for a while. So between the test mass and the Earth, definitely attract. Now, then, if I want, that means I'm just trying to show you the field strength of the Earth at this point is to the left. Now, to find the field strength of the Moon, I must now ignore the Earth. I put a test mass here, it will be attracted to the Moon also, ma. You see this Fm here? The force exerted by the Moon on the test mass is to the right, right? So the field strength of the Moon at this point is also to the right. So you look at the two field strengths, the field strength of the Earth to the left, field strength of the Moon to the right. If they are vectors, should I plus or minus them?
Minus.
Okay, so opposite direction we minus. So if both of them have same magnitude, wouldn't they cancel out each other then?
Yeah.
Try to imagine this now. Let's say you're attracted to this, you're attracted to this. So somewhere along here, right, both pull you the same magnitude. So when what happens? You don't move on. You understand now? So there will be a point where you got zero field strength. Do you understand now? But just for discussion's sake, where do you think this point would be? Would it be right in the middle, near the Earth or near the Moon?
Near Moon.
Think carefully. In the middle, who will win? Earth will win. But if you want to be balanced, you must move towards the Earth or move towards the Moon. Moon. Because the Moon is weaker, so you must give it more advantage. Go towards the Moon and then can balance. So far so good.
Yes.
Okay, so this is how you explain this here. The force exerted by the Moon and the Earth, the force exerted by the Earth and the Moon, okay, or by the Moon and the Earth, same lah, on a test mass, will be in the opposite direction. Will be in the opposite direction. Okay, so the field strength of the Moon and the Earth, or they say the Earth and the Moon, so the field strength of the Earth and the Moon will also be in the opposite direction. Will also be in the opposite direction. So they may cancel out each other. Now for the next part, you want to find the distance from the center of the earth where the field strength is 0. Now remember, from the center of the earth to a point. Now just now you said that most likely the point is nearer to the moon, right? So assuming that the distance from the earth to this point is x, what is the distance from the moon to that point? Now they told you the total separation is 60 RE, so wouldn't it be 60 RE minus x? So the field strength here is 0. Now field strength being a vector and they are both in opposite directions, so you got the minus, right? So your working is like this. The field strength of the earth minus the field strength of the moon will give you 0. So the field strength of the earth is gm over, now the m must use the mass of the earth. The distance is from the earth to that point, which is x, right? To find the field strength on the moon, you must use g times the mass of the moon. Then you must divide by the distance, right, which is here, 60 RE minus x square. Understand? Because this distance is from the moon to here. That's why you must use this distance here. Is equals to 0. Now, listen carefully. You can do something to make your calculation simple. Because it's equals to 0, we can cancel the g, right? After we cancel the g, we get this. Substitute the mass of the earth, mass of the moon. Now, then you bring this over the other side. So then it becomes equal. No need to put negative, right? Then you can do something that is legal in physics but illegal in maths. Because in maths, your teacher won't let you square root both sides. You must cross multiply and find the factor. But in physics, we square root both sides straight away. Correct or not? Okay. You square root both sides, then the square here, when you square root, just becomes 60 RE minus x, right? And the x squared become x already. This one you square root, this one you square root, then you can find your x. So now here, they want you to sketch a graph to show variation of gravitational field strength. Now how do you find, how you plot the gravitational field strength? Now firstly, the gravitational field strength at the surface of the earth will be towards the earth, right now? Which is to the left, right now, according to your diagram. But the field strength at the surface of the moon will be to the right towards the moon, no? Which is why I have two values, one positive and one negative, to show you the opposite directions. Do you understand? That means if I take the field strength at the earth surface to the left and positive, then it means the field strength at the moon surface to the right must be negative. But which one is stronger field strength, at the surface of the earth or surface of the moon? Earth. So therefore the magnitude also, this must be higher than this magnitude. Do you understand? But how do I know it is a curve? That's the question. Remember the formula for field strength is what? So it's a 1 over r squared graph. Right? That's why it's a curve. Do you understand? Okay.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.